Hello, this class is about groundwater, so this is your introduction to groundwater. Hopefully after this class you'll be ready to understand the field trip that we'll have the week after next, and of course the lab that will follow. First of all, the water cycle is something that you've seen a lot, and remember that there's certain elements that you need to remember that we are adding now. So you have precipitation, you have evaporation, evapotranspiration, and you have part of the water infiltrates, and some of that water is going to the roots, some water goes into the aquifer, and of course that takes a long time for rainwater to reach the aquifer, but then we pump water a lot faster than we can replenish. This figure here is a little more detailed, and we will see this figure again as we talk about surface water. So what we have here is a water table that you can see here, and in this case the lake follows the water table, and this zone here, the unsaturated zone, is called the vadose zone, and that zone goes back and forth between saturation and non-saturation, but of course the zone of saturation will be under the water table that you have. And you can have some springs, you can have wetlands, and of course the precipitation in form of snow or rain, and you have here bedrock with cracks and crevices, infiltration. So you can have water storage among the soil particles, but also in some of the cracks and crevices in the bedrock. This shows the big aquifers in the US. You will have this slide presentation, so I recommend that you go to the link shown below and you'll see a lot of the aquifers in the US. As I mentioned, groundwater can be stored in varying quantities below the surface in permeable water-bearing geologic formations, and these are known as aquifers. And we have two types of aquifers. We have confined aquifers and unconfined aquifers. And the difference between confined and unconfined is that in the unconfined you have a free water table, but in the unconfined aquifer you don't. So for example, here you have a water table, and this water table can go up or down because there's no layer of rock or impermeable layer of soil that keeps it from going up and down. However, here we have a confined aquifer, and it's separated from the rest of the aquifer, or from the top, by an impermeable confining stratum. So this is confined. In many confined aquifers you can have high pressures, and then that's when you have artesian wells and springs without having to pump. Okay, so those are come under pressure, and you might not need to pump them if the pressure is big enough and not as deep. So in the case of unconfined, for sure you will need a pump to drain the well. Groundwater can be stored in different ways, and basically for normal soil, not with crevices and cracks in the rock, but in normal soil conditions, the storage of water depends on the porosity of the soil. The porosity is the ratio of volume of opening or voids to the total volume, and the porosity depends on factors such as packing, sorting, and grain shape. When you take soil mechanics, you'll talk somewhat about porosity as well. So you have your soil grains, and then the water can be stored in the voids of the soil. Whenever you have loosely or uncompacted soil, you will have more porosity than if you have compacted soil. So, as I mentioned, porosity is the ratio of volume of opening or voids to the total volume. So this is the equation and the symbol for porosity. There is what we call primary porosity and secondary porosity. The primary porosity is what we mentioned, which is a function of the composition and structure of the rock. The secondary porosity occurs due to weathering, faulting and folding, and other phenomena which creates fractures, fissures, or caverns within the rock formation. So here you see some caverns, and this kind of formation is really difficult to predict where you'll find water, which is the case that we have in Haiti, where you can have a well that you drill and 20 feet from that well get water, and then 20 feet farther not any water, because what happens is that you generally are hitting caverns in the limestone, and it's not so easy to determine where those caverns are. So you might just be lucky or not lucky. These are common ranges in porosity for clay, silt, and of course one of the important things is that porosity changes with the type of material. Of course, it also varies with the compaction. So here you have a uniform sand 0.3 to 0.4, and then you have gravel and sand mixed or limestone 0.01, 0.10. What does permeability have to do with it? We have started a lab to calculate the permeability conditions in the experimentally. We'll see today how to calculate permeability from field conditions. But whenever we talk about permeable condition, that means those buoys might be connected or interconnected or not connected at all. So you can have some porosity and not have as good permeability. But see, if you have this soil, the water does not go in a straight line. It curves around all the soils. Okay? So the permeability will change depending on that route of least resistance. So we have talked two things, porosity and permeability. So they are different. They're related, but they're different. Porosity is a measure of how much of a rock is open space. This space can be between grains or within cracks or cavities in the rock, and then permeability is a measure of the ease with which a fluid, water in this case, can move through a porous rock. So here there's three different types of rock formations. You have shale, sandstone, and limestone. And this helps you understand from shale rock, if you have oil, it's difficult to get oil from shale formations, and that's where you can do some of that fracking to try to push the oil out of there. Of course, here you have water. So you can see how this partly explains why the flow rate for shale is less than, for example, sandstone. You'll have the slides, and I encourage you to look at these simulations, and you'll see those three formations and their porosity and permeability. Okay, so let's review some concepts here. Darcy's law. Remember, we talked about Darcy's law, which tells you that the velocity across a soil is going to be dependent on the hydraulic gradient, dH, in the direction of the flow path dl. So dH over dl, and K is the proportionality constant, which is the coefficient of permeability, or also called hydraulic permeability. So this velocity here is what we call the apparent velocity. It's not the true velocity. K depends on the aquifer properties and the properties of the fluid, and here you see an example of an empirical equation that shows you how two parameters, the C times D squared, the diameter is the D of the soil particles, which is a property of the aquifer material, that means the soil, and then you have the specific weight and the viscosity of the fluid. So you can see clearly how it's dependent on those two, the aquifer properties and the properties of the fluid. How do we determine K? Well, we mentioned in the lab, empirical equations, experimental, we did the constant head and of course field conditions, and we'll see that today. The lab that you'll be doing this week, you will calculate the permeability coefficient using a steady flow to a well. In this case, you'll have an aquifer that you are going to assume it's homogeneous, that properties are uniform, isotropic, meaning that the permeability is the same regardless of the direction of flow, and that the wells penetrate the aquifer. Okay, these are different coefficients of permeability ranges that you have already seen, and as I mentioned, the Darcy's law gives you the velocity, which is the apparent velocity, but it's not really the seepage velocity. Remember that the seepage velocity is a velocity, so it's distance over time. But the distance is not always a straight line, so that distance can vary. Okay, so for example, you have, if you don't have any soil, you have an area, so that Q over area, but then now the porosity tells you how much of that area is covered by soil, because the water can only move through the voids. So that area now is going to be multiplied times the porosity here. Okay. Work on this problem, which is very similar to what you did in the lab, so I'm not going to go over that. This is example 7.1. So review it and study it, and the reason I'm not reviewing it is because that's part of your lab work. So let's continue with the groundwater and groundwater recharge. And remember that, as I mentioned, groundwater is replenished by percolation from rain and snow, as you saw in the water cycle. And I just want to show this cross-section here. You have your zone of saturation, which is usually devoid of oxygen, and then you have your zone of aeration because you have infiltration that goes up and down. You can have what we call aquicludes, which are just impermeable layers where water can accumulate. Okay, and then of course you have your topsoil. The boundary between the two is the vadose zone here that can go from saturated to unsaturated. Modeling groundwater when it's saturated is relatively easy, but modeling in this zone is not so easy because of the changes. So you can have different types of aquifers. You can have confined aquifer and then an unconfined aquifer and so on and so forth. And then you can have rivers, and depending on the time of the year, you can have the groundwater recharging the river or the river charging the aquifer. Okay, and for example, in our case, what you'll see is if there's no water in the rivers, the groundwater is recharging the river in some parts. So in the winter you still see water in the Rio Grande, but then in the summer during irrigation season you have your stream flowing, and that helps to recharge part of the aquifer. However, the irrigation district does not want to recharge the aquifer. They want to deliver the water, and that's why they line with concrete many of the canals. You can have situations in which they're disconnected, of course. Factors that affect the rate at which water permeates to the water table, of course, the moisture content, the soil texture, the soil type, the presence of impermeable layers called fragipans, or soil compaction. Now let's talk about unconfined and confined aquifers, so we can do some example problems, and these problems I took them from the book. So if you have any questions, refer back to the textbook. So here you have on the left an unconfined aquifer, so you have the water table, and the notation here is extremely important. Remember that you need to know what is what in these cases, so you make the appropriate substitutions. So let's take a look at this. So this is the original water table, and in an unconfined aquifer, as you pump water, you have what we call a cone of depression, which is this cone here. Let me delete this. So I'm showing it in a 2D, but remember that the cone of depression is a circular shape, and it's like a cone. So let me erase this. So what we have is here you have a well, and it tells you the diameter. So if you have the diameter, this would be the diameter of the well, that's the W, and then here you have the radius of the well. At that radius you have what we call here the drawdown, okay? And this distance here is going to be, let me put it here, it's going to be H0, which is the original level, minus H. If it's at the well, it would be HW, right? So that is the drawdown, and it's S is the drawdown. You can find the drawdown at any distance from the well, right? So if I look at any distance X, I can find the drawdown, which would be always the H naught or 0 minus the H. Okay? This here is R0, so this is the distance from the cone of depression. So after that, you don't have any depression. So if R is larger than or equal than RO, you are away the cone of depression. And so this would be like the radius of influence. Anywhere within the radius of influence, there's going to be a drawdown, and anything that you do in that area will be affecting that cone of depression. Okay? So here you have the HW that I mentioned, which is the one that goes here. Remember, you can always stop and look at the notation. Now here we have an impermeable layer to the right, so this is a confined aquifer. And of course, whenever you have a confined aquifer, you have all that water, but you'll have the actual piezometric surface above the confined aquifer, and the cone of depression will be created with that water that's above the confined aquifer. The notation is exactly the same as for the unconfined aquifer, and here you have the RO, HO, and then you have H, and of course HW. The only thing that's different is that now the thickness of the confined aquifer is B. Okay, but you have the same here notation, and then this at any distance R, this is your H, and then you have your drawdown also, which is S equals H0 minus H. So this is the drawdown, okay, and then this is of course the drawdown as well. So let's start with confined aquifers. So we will use Darcy's equation, and we'll use plane polar coordinates. The B is the thickness of the aquifer, and using Darcy's equation, it's derived to determine the flow rate in confined aquifers. I'm not going to work on the derivation, but this would be the equation that we're going to be using, and then you have H naught and R naught, but you can also find H and R, so it's at any distance, not just RO, but at any distance. You have here H, so it could be at any distance. Okay, so this is kind of the generic equation. So this is just repeating what I just said, how you can have the equations. So So let me continue with the recording here. What I just said, I apologize for the interruption. So there's a term that's used, transmissivity in a confined aquifer, which is the hydraulic conductivity times the thickness of the aquifer. If you'll remember, this has units of feet per second or meters per second or meters per day or feet per day, but then whenever you multiply times the thickness, so now you'd have square feet per day, square meters per second, square meters per day, or square feet per day. So instead of showing the hydraulic conductivity and the thickness, we just substitute with a T for the transmissivity. Okay, and it makes sense. The transmissivity is an area per time, so rather than a velocity. Okay, so here is the equations again for a confined aquifer. We already went through the notation here. So for any piezometric head, we look at a distance and we can calculate the drawdown, of course the head and then the drawdown. So let's see this example. A discharge well completely penetrates a confined aquifer that is pumped at a constant rate of 2,500 cubic meters per day. The aquifer transmissivity is known to be 1,000 square meters per day. The steady state drawdown measured at a distance 60 meters from the pumped well is 0.8 meters. So determine the drawdown at a distance of 150 meters from the pumped well. So you know that this is a confined aquifer, so immediately you know which equation you need to use. And then look at the givens. Okay, so you have the steady state drawdown, which is 0.8 meters, and that's at a distance of 60 meters. So these two are related. The flow rate is 2,500 and the transmissivity. So if you look at this, we have this, we have the transmissivity, we have this, and then we have to determine the drawdown at 150 meters. So we just make the appropriate substitutions. Here you have 0.8 and 60, and then you have to calculate the drawdown at 150. So you substitute 60 over 150, and here you have the drawdown is 0.435, so this is at a distance of 150. So what you have here is, if you know at a certain distance what is the drawdown, so what we have here is that at a certain distance here, that this distance was 60 meters, the drawdown here was 0.8 meters. So if I have the drawdown and the distance and the transmissivity, then I can calculate the drawdown at any other distance. Okay? Now let's say that you have more than one well, and what happens is that the effect is compounding. So let me just draw something here. I can have a well, and this is my radius of influence, right? And then I can have another well here, and then this can overlap. And so